All right, so we're going to finish up with 5-6 trends in periodic properties. So we'll use the electron configurations of elements to explain the trends in the periodic property. All right, so valence electrons. Valence electrons are those that carry the highest energy level, okay, and they're the things that are really reacted with when we talk about chemical reactions. It is very dependent on the number of valence electrons. So if we are, it's related to the group number of the element and determine the chemical properties of an element. Okay, so for example, we have phosphorus. Phosphorus has 5 valence electrons. Well, how can we determine that? Well, if we look here, the highest orbital, okay, so we have 3s2 and 3p3. Well, 3 plus 2 is 5, meaning to be stable, since we're looking for normally 8 in the octet rule. Okay, well, how many more elements do we need? Well, we need 3 more electrons. Did I say elements? How many more electrons do we need? 3 more electrons to make this a stable configuration. All right, all of the elements in a group have the same number of valence electrons. So in the case of group 2A, beryllium, magnesium, calcium, strontium, all have the same number of valence electrons, and we can see this. At the very end, we got 2, 3s2, 4s2, and 5s2, okay? So if we looked at the very end, well, I should have not gone that far. Let me erase that. Okay, but if we look and at the very end, and this will become more clear on some other examples, but highest energy levels, right there, right there. So that tells us how many valence electrons. And every group has the same, elements of a group have the same number of valence electrons. So if we look down here, okay, hydrogen, lithium, sodium, potassium, hey, they're all S1. They all have 1 valence electron. If we come over to here where oxygen, sulfur are at, we can see that the highest energy level is 2s, 2 and 2p4. This is 3s2 and 3p4. This is 4s2 and 4p4. But regardless, 2 plus 4 is 6, meaning we have 6 valence electrons. Fluorine, wood, chlorine, bromine, 7. Pretty easy to decipher. Now, if we look down here by the noble gases, which I always call the cool kids, with the exception of helium, which has 2, which we know the first orbital can only have 2, all of the rest of them equate to 8, all right? And that's what they're looking for. So they're stable, they're inert, they don't react because of this stable electron configuration, okay? Having 8 valence electrons. All right, so if we look at oxygen, and we can go back and just check the table back there, oxygen, all right, so we look back to oxygen, okay, here's oxygen right there, all right, 2 plus 4, well, that means oxygen is going to have 6. If we look at aluminum, all right, there's aluminum right there, and 2 plus 1, so that's going to be 3, and then chlorine is going to have 7, and because I know it's in 7, and also you'll even notice, which is convenient, the periods, the columns, so 2, 3, 4, 5, 6, 7, 8, right? Valence electrons. Group 6A, it says go to group 6A. All right, how many valence electrons? Well, we can now decipher just based on the group, right? It's going to be 6. All right, what about 10? Well, let's go find 10. And what is the periodic element for 10? Anybody? Not getting any responses. I don't understand. 10 is SN, okay? So we'd have to go to the periodic table and then look at SN, all right? And it is valence electrons of 4. All right. So I'm hoping this is jiving so far. It's making sense. All right. So now it says state the number of valence electrons for each. Okay, well, what do we look for? The highest filling energy level. So right here we have 5. If we look at here, our highest energy levels are the 4s. Okay, remember, we'll drop down a level to fill that out first to make it stable, because it's a more stable place to be. Electrons invariably want to be stable. So in this case, we've got 2 plus 4, so we've got 6. And right here, we've got our highest levels 2, and we go 2 plus 5, which is 7. So 5, 6, and 7. Okay, so just because there's a number in between does not mean those are valence. We always go with the highest energy level. So we talked about this in class already, but the Lewis dot structures, or electron dot structure symbols for magnesium, it can be any variation of these, right? Here we go. But basically, magnesium has highest order, level 3, right? And 2 electrons. So it's configured by 2 dots, okay? So here's an example of Lewis dot structures. I believe I used in class carbon with 4 hydrogens to create methane, and how they kind of fit together like a puzzle. So hydrogen would look like this, and then carbon would look like this, becoming stable. All right, so atomic size is determined by the distance of valence electrons from the nucleus. Okay, so as atomic size increases, okay, or as we go down, okay, but as we go to the right on the periodic chart, it actually decreases. But if we go down even to the right, what's happening to our atomic size? It's still going up and up and up. So the atomic radius of the nucleus, okay, radius, just going to math, half the diameter, right there, and right here. All right, and we got lithium, sodium, and potassium. Basically, as it is going down, the atomic size is increasing. And this also relates to the reactivity level, okay, of the chemical as well. Like a good assignment for you to see what I'm talking about with energy is look up videos of throwing lithium in water, throwing sodium in water, and throwing potassium in water. And maybe Lisa will be kind enough to demonstrate, but who knows, okay? And basically, the reaction becomes greater and greater and greater as you go down the column in the periodic table. So lithium has, a kind of burning reaction. Sodium, slight explosion. Potassium, an even larger explosion, and so on and so on and so on. So the atomic radius, as I said, decreases going from left to right across the period as more proteins. Wow. Protons increase the nuclear attraction for valence electrons. Okay, so the more protons we have, the more attraction we have to the nucleus. So it's going to bring it in tighter, all right? So which one of these, if we had a periodic table, which would have a larger radius? Lithium or potassium? Okay, lithium or potassium? Well, we're going down, right? So, what do you think? Yep, it's going to be potassium. All right, now, potassium or bromine? Well, potassium is to the left of bromine, so I'm going to guess it is bromine, okay? And finally, we have phosphorus or chlorine. All right, well, what are we going to see? We've got phosphorus right here, and to the right of it is chlorine, so that means that phosphorus will have the larger size atomic radius. So let's check this out. Let's make sure. Yep, potassium is larger than lithium. Potassium is larger than bromine, and phosphorus, because it is to the left of chlorine, will be larger than chlorine. So ionization energy is the energy it takes to remove a valence electron. Okay, how much energy does it take to either remove an electron? So if we think of sodium, okay, and we just have this 1,3s orbital there, okay, and so we got energy ionization, which will give us sodium positive charge because it is going to lose an electron, okay, an electron coming off. So metals have 1 to 3 valence electrons, so they have low ionization energies. Non-metals have 5 to 7 electrons, so they're going to have higher ionization, because if I want to rip 1 electron away, it's not a big deal. If I'm going to try to rip 5 to 7 away, it's a much harder time. So noble gases have something called complete octets. It's called the octet rule, with the exception of helium, just because it's so small as 2 valence electrons. But the rest of them have 8, okay? So they have the highest ionization energies, and that's simply because they are stable, they are happy, they don't want to react, okay? So if I said which is more reactive, or has a higher, it's harder to get it to ionize, I guess. Metals, relatively easy. Non-metals, much more difficult. And if it's noble gases, or at least to create cations, noble gases, well, they don't. They're inert. They're pretty stable. Okay. So now let's select in each pair which has a higher ionization energy. Okay. So lithium or potassium. Okay. Potassium or bromine or phosphorus or chlorine. Well, ionization energy, we're going to definitely say that bromine and chlorine are going to have higher ionization energy because they have more electrons. Now, what about the case of lithium and potassium? Well, aren't they in the same series? So lithium is going to have a higher ionization energy than potassium because it is lower or higher up than is potassium. Bromine and chlorine, because it is to now the right of potassium and phosphorus, that it is going to have a higher ionization energy. Okay. So elements with high metallic character lose their electrons easily. Elements that are metals lose their electrons easily. Metalloids lose their electrons, but not nearly as easily. And remember, metalloids are the steps right there, okay? And then non-metals do not lose their electrons easily, okay? They tend to gain them, bring them on, you know? So, summary of the trends of the periodic table, okay? Periodic properties, top and bottom of the group. Valence electrons remain the same, the amounts. The atomic size increases as we go down. Ionization energy decreases because the further away they are from the nucleus, the easier they are to rip away. And metallic character increases because the valence electrons are easier to remove when they're farther from the nucleus. So left to right, across the period, valence electrons increase because we're moving towards noble gases. Decreases the number of protons as the number of protons increase, which strengthens the attraction. Increases ionization energy increases and increases the number of protons, strengthens the attraction of the nucleus for the valence electrons. And metallic character decreases as the number of protons increase, which strengthens the attraction to the nucleus for the valence electrons to make them more difficult to remove a valence electron. All right, so in the end, this is kind of our concept map of what Chapter 5 has been all about. All right, nothing too difficult, pretty straightforward. Like we talked about, the orbitals are probably going to be the most difficult area for you guys to understand, but I felt good when we left class today that you guys had a pretty solid concept of what was going on. And we'll just briefly touch on that at the beginning of lecture on Thursday. And yeah, we'll finish that up then, and then move on to Chapter 10. So I hope you guys have a good evening, and see you soon.